Welcome everybody. Racing the board. All right. Let's see. Let me get my screen pinned here. I need to change my background. Sorry, one sec. Yeah, I can fix this. Okay, cool. Here's the chat. And here is the attendance link as usual. All right. What do you guys want to talk about?
Can we go over the finding the max and mins of direction, max and mins of multivariable functions? We finally started going over the first derivative in Rodriguez's class today.
Okay, so when you say, well, because I was watching this class today, so you guys definitely, like, you talked about finding like the stuff we did last class, like with the D and the things like that.
Mm-hmm.
Yeah, totally. So I will mention, I did make like 2 or 3 videos about this on YouTube, so definitely go look at that as well. There are lots of great examples. Let me just grab one from, yeah, I got lots of sources here. Where'd you go? I don't like the chat here. Sorry, my chat's all weirdly popped out. 1 second. Or not. What is the way to fix that? Oh well. I can't fix it. I'm not smart. Oh well. Okay, let's see here. Did I do that one last time? No, I did not. Okay, cool. So let's do a slightly more complicated example. Let me ask, I just want to make sure everyone can see this pen. Getting a little on pens, I'm going to have to go back to campus and grab some new pens. But let's see where am I going. So here's my function. Z equal to xy squared minus x squared y plus x minus y. And actually, let's think for a second here. Maybe I want to. It might just be a nice link here. Sorry. And sorry, so I feel like that example might be just a little harder than I want to start with. There we go. Sure, let's look at this one. So we'll do this one next, but let's do this other one first. And again, just so everybody gets it, you guys have been doing great with the attendance. I think everyone is signing appropriately now, which is awesome. Let's look at this function instead. F of xy equal to x to the 4th plus y to the 4th minus 4xy plus 2. And before we get started on this, just want to let you know, I did also made a couple videos of implicit differentiation, but I think it was kind of the wrong thing. It was like finding dy dx. And I think I finally realized that you guys were actually asking about finding like del z del x and del z del y. So I made a video about that too. So there should be lots of implicit stuff up there. Hopefully one of them will fit the bill. We can also do something today if you guys want. So to find the maxes or mins, so we usually say find and classify all extrema. Again, we're going to find the critical point. So when we find the critical points, they're setting each of the partials equal to 0. Now, Rodriguez talked about it as setting the gradient equal to 0, which is also true. If you're setting del f equal to 0, you're really just setting the partials fx and fy equal to 0 each, right? So you really solve, right? That's literally the equation we were doing last time. Set fx equal to 0, set fy equal to 0, and find the set solutions that are solutions to both of them at the same time. So my partial with respect to x is going to be 4x cubed plus 0 minus 4y. I'm going to set that equal to 0. And my partial with respect to y is going to be 4y cubed minus 4x equal to 0. So solving the first one, I'm going to get 4x cubed equal to 4y. So y is going to equal x cubed. And so currently, there's an infinite number of possibilities, right? 0, 0, 1, 1, 2, 8, 3, 27, et cetera, et cetera, et cetera. But those aren't all possibilities for this equation as well. So now we're going to set this equal to 0, and we're going to plug in that for y. So I've got 4 times x cubed minus 4x equal to 0. Yeah, sure. So this is 4 times x to the 9th minus 4x equal to 0. Factor out of 4x. Okay, so what are my solutions? Well, x can be 0. And here, x to the 8th minus 1 equals 0. What can x be? Well, certainly 1. Is that it? No, we can also get negative 1. And you can either do this by factoring, right? X to the 8th minus 1 does factor further, right? But you can just see it's 1 and negative 1. I mean, there is more work you could do, but eh. Okay, so then, now that well, so I should say, our critical points are x equal to 0, and if x is 0, then y is also 0. X equal to 1, if x is 1, y is also 1. If negative 1, if x is negative 1, y is also negative 1. That doesn't always happen, but in this example it does. So all of our coordinate pairs happen to have the same x and y value. Okay, and now we're going to classify them. So I'm going to erase all of this. Right, found our critical points. I'm going to erase this too. Now we're going to classify them by looking at evaluating them at the determinant of Hessian. So this capital D, which is again fxx times fyy minus the mixed partial squared. It shouldn't matter which way you do the mixed partial, because it should be the same for any of the functions we're dealing with. Let me move this out of the way here, one sec. Okay. And so, let me see here. So fxx is going to be 12x squared. I feel like we might have done this one before, or at least one very similar. Fyy is going to be 12y squared. And fxy is going to be negative 4. And fyx is going to be negative 4. You can even simplify this before we write it out, before we evaluate it. This is going to be 144 x squared y squared minus 16. So if I plug in 0, 0, I get 0 minus 16, which is negative. And if this capital D is negative, what does that mean? What kind of critical point do we have? Do we have a maximum, a minimum, or a saddle? I should have you guys vote. I should have made a poll. So I will tell you it's a saddle. So whenever D is negative, it's a saddle. So we definitely have a saddle at 0, 0. Okay. So then at 1, 1, well, 1, 1, we're going to get 144 minus 16. Again, I don't really care what the number is. I just care that it's positive. So if D is positive, we don't have a saddle. What do we have? Well, it's kind of one or the other, meaning you either have a saddle or you have a max or a min. But then if it's a max or min, you have to do more work. So it's definitely a max or a min. And then we look at the second partials. So here's my second partial, fxx. Now, here's what I see right away. fxx is 12x squared. Whenever I plug in for x, it's going to end up being positive. Right? Whether I'm plugging in x equal to 1 or x equal to -1, 12 times x squared is going to be positive, which means the second derivative is positive. Which means it's concave up, which means we have a minimum at that point 1, 1. And the same is going to be true for -1, 1. Sorry, -1, -1. So you plug in -1, -1, you're going to get the same value here, 144 minus 16, which is going to be positive. And then when you evaluate the second partial, the second partial, fxx, I should really write fxx at positive 1 here. fxx at -1, -1. Well, again, plugging in -1 for x into the second partial still is going to give me positive 12, which is still positive, which means I still have a minimum because it's concave up. So I have a minimum at -1, -1 as well. And we might look at Desmos for just a second and graph this, because I feel like this graph might actually show up all right. So let me take a look real quick here. Let me share my screen. I'm gonna move my boxes around. Sorry, I got too many boxes. Okay, let me share my screen. Yeah, the whole screen, please. Yes. Oh my goodness. Okay. And if we graph this, x to the 4th. Oh, okay. X to the 4th plus y to the 4th minus 4xy plus 2. You gotta do the 3D graphing maybe, James? Okay, sorry. Good job. There we go. I already have this one. Okay, sure. So really we're looking at fun times. X to the 4th plus y to the 4th minus 4xy. Ooh, exciting, plus 2. And if we look there, so if we spin it around a little bit, you can kind of see, oh yeah, totally, right? Look, there's the minimums at -1, -1, and +1, +1. And right here, there's a saddle at 0, 0, comma 2, right? 0, 0, plus 0, plus 2. So yeah, that's cool. I like that. You can totally see that there's a saddle there. If we go, that might be helpful. Yeah, oh wow, okay, fun times. Yeah, you can see a saddle. Okay, great. That's okay, enough of that. So, yeah, it's kind of nice to see the graph and kind of see that it actually agrees with what we're finding there. So let's do one more example. I'm going to make you guys participate a little bit more in this next one. So the thing with these is it can get challenging to find the critical points. But again, you're just setting each of the partials equal to 0. So fx here is, so differentiate with respect to x, I'm going to get y squared minus 2xy plus 1. I'm going to set that equal to 0. And then I want you guys to find fy. Find the partial with respect to y. So hopefully that's going well for you guys. Looking at the graph of this thing, it looks super neat. Hopefully you're finding this. Let's see, so the derivative with respect to y is going to be 2xy minus x squared minus 1. Something to notice about this, in case you're curious, this is kind of an example of, like, there's some sort of symmetry here. I think it's an odd symmetry. Like if you replace x with negative y or y with negative x or change them, you get kind of the same thing, right? Because these are essentially the same. If you interchange x and y, but one's negative, these are kind of the same. So there's definitely some symmetry here. The derivatives definitely look very similar, but I'm getting, if I switch x and y, this would be 2xy minus y squared minus 1, which is essentially the negative of that. So often these problems have this kind of symmetry to worth looking out for. And then I'm going to try and solve this. So let's see. Let's work with this second one. Typically, what we're trying to do is we're trying to isolate one variable. Since I see multiple x's and only one y, I'm going to try and isolate y. So I'm going to add this over here. So I'm going to have 2xy equal to x squared plus 1. And then I'm going to write y equal to x squared plus 1 over 2x. And I guess I could actually look at the solutions and see if that's what the person who did this was doing. I mean, I lost where they were. It's all right. It's okay. I don't remember where I got this question from. It's fine. And then in a similar way, so we can, actually, I probably should. Sorry. I've only got like 1,000 tabs open here. Where'd you go? Good question. Oh, I think it's right here. Okay, yeah, that's what I thought. Just want to make sure. So then we're just going to plug this in for our y's in the other equation. So right there and right there. And it's going to get a little bit messy. So I'm going to have, all right, so, yeah, a little bit messy. So y squared, that's going to be x squared plus 1 over 2x squared minus 2x times y, which is x squared plus 1 over 2x plus 1 equal to 0. Yeah, that's messy. Okay, that's fine though. So then we're going to try and solve for x. All right, so I would probably write this as x squared plus 1 squared over 4x squared. We luck out here, things cancel. So you get minus x squared minus 1, right? So we distribute, plus 1 equal to 0. These cancel. So then you've got x squared plus 1 squared over 4x squared equal to x squared. Multiply both sides by that. Multiply this out. X squared plus 1 squared is x to the 4th plus 2x squared plus 1 equal to 4x to the 4th. So then bringing everything to this side, I'm going to get 0 equal to 3x squared, right, so 3x to the 4th plus, minus 2x squared minus 1. And hopefully it factors, I'm pretty sure it does. 3x squared plus 1, x squared minus 1. That seem right? Let's see, I get 3x to the 4th, I get a minus 3x squared, I get a plus x squared, it's a minus 2x squared, minus 1. Looks good. And so then this part here is never equal to 0, because 3x squared plus 1 is always bigger than or equal to 1. So my only solutions are this part here equal to 0, which is going to be x equal to plus or minus 1. That's a lot of work. All right, so then if x equals 1, y is going to equal 1 plus 1 over 2, which is 1. And if if x equals negative 1, I bet we're going to get negative 1. Y is going to equal negative 1 squared is 1 plus 1, which is 2 over negative 2. So my critical points are 1, 1, and negative 1, negative 1. Which I don't know. I don't think I could have guessed those. But we can definitely see that it's true. Right? If x and y are both 1, you get 1 minus 2 plus 1 is 0. And you get 2 minus 1 minus 1 is 0. So it definitely works. All right. Let's classify them. So go ahead and start finding fxx and fyy and fxy. I'm going to flip, yeah, sure. So back to what we had, sorry. Fx was minus or minus 2x plus 1. So those are my second partials. Fxx is negative 2y because I took the derivative of this with respect to x and got negative 2 times y. Fyy, derivative of this with respect to y is 2x. And fxy, differentiating this with respect to y, I get 2y minus 2x. I always, if I feel like I might have made a mistake somewhere, I often like to check and see if my fyx is the same as my fxy. So if I find fyx, just to be sure, I get, let's see, differentiate this with respect to x. So I get 2y minus 2x. Check. Okay, good. I feel better about that. It's probably right if those match up. So now, calculate the determinant of the Hessian, which is just fxx, fyy. And we're going to plug in our critical points. Well, first, actually, we're going to write it out. So it's going to be negative 2y times 2x minus this quantity squared. So that if we still, I don't really want to simplify it. We could simplify it. I don't think that's super. I mean, you could, I would, if I was going to simplify, I would only do this. I don't really feel like multiplying that out is helpful. So let's plug in 1, 1. So I plug in 1, 1, I get negative 4 here. Minus 2 is 0 squared. All right, so what kind of thing do we have at 1, 1? Do we have a max or a min, or do we have a saddle?
Saddle point.
Yeah, definitely. And I think we have the same thing at negative 1, negative 1. Plug in negative 1, negative 1. I still get negative 4 times negative 1 times negative 1 is negative 4. And 2 times negative 1 minus 2 times negative 1 is still 0. So both are saddles. Because both of them have this being negative. And I'm just trying to lighten here. It's a little bit dark for me. If we look at, so I'm going to share my screen again. If we look over here at the graph looks cool, by the way. I was just, where'd you go, graph? Yeah, so here's the graph of it. It's pretty neat looking, I think. And if we rotate it around the z-axis, you can kind of see how, yeah, look, so that's a saddle right there. And there's a saddle over there as well. Kind of cool. I think this might be what they call the monkey saddle, where, so like if you look at this part here, you can imagine like a monkey sitting on this facing forward and its tail would be falling over the back, right? You need kind of like that, right? A regular person saddle wouldn't be good for a monkey because there's nowhere for the tail to go, but this is called the monkey saddle because there's like kind of 2 leg holster parts and then it goes back like that. It's kind of neat. Okay. What else should we do? I could do an implicit differentiation example if you guys want. You guys like? Sure. All right. I forget if this is the one I just came up with. No, that's a different one. Okay. Oh, it was somewhere else. Okay, and then I think I'm going to start. What time is it? Yeah. So we'll do implicit differentiation. And then if you guys have other questions, I'll address them. But if not, I'm going to start moving towards systems of linear differential equations. So, oh, I had an example. I'm just going to make something up. So this is very much like what we did in 17A, where you just have all your variables mixed together. So let's say we had something like x to the fourth z cubed plus y squared z equal to natural log of x cubed plus z. And I want to find my partials of z with respect to x. Seems we have the same desktop background. Sorry, reading private messages out loud. That's cool. Yeah, it's a good. I like my desktop background. It's a good one. Brain work. Okay, come on. So the idea here is that z is a function of x and y, right? So x and y are still both independent variables, but z is dependent upon them. So just like way back in the day, when we did like this, x squared y plus 4 x cubed equal to y to the fourth, and we differentiated something like that, we were pretending that y was a function of x. And so when we differentiated this, we would get like 2xy plus x squared y prime plus 12x squared equal to 4y cubed y prime. Same kind of thing is going to happen here. So if I'm finding del z, del x, or I probably would rather write zx because it's a little bit easier, I'm thinking that z is a function of x. Also y, but we're differentiating with respect to x. So when I differentiate this, I have to use the product rule because I've got a function of x times a function of x. So the derivative is going to be 4x cubed times, leave that part alone, plus, now we do it the other way, x to the fourth times the derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. I think you do have to be extra careful if you write it this way because it can be easy for a z sub x to turn into a z times x accidentally, so make sure you're very careful with your notation. Let's see, plus y squared times z, the derivative is just going to be y squared times zx, because for this partial, you're treating y like a constant. So this is just like 5 times z, and the derivative is 5 times the derivative of z, equal to the derivative of the natural log of some stuff. It's 1 over the stuff times the derivative of the stuff. The derivative of x cubed is 3x squared. The derivative of z is zx. And after you do all that, the rest is just a terrible algebra problem. So I'm going to simplify a little bit. And there's actually 2 things I need. Oh, that's smart, James. There's 2 things I need to make sure I do. Sorry, I'm trying to end on my knees a lot at this board just because it's easier to write down here like that. So let's see, I've got 4x cubed z cubed plus 3x to the fourth z squared times zx plus y squared zx equal to, I need to distribute this to each of those so I can break up the thing that has a derivative and the thing that doesn't. So I've got 3x squared over x cubed plus z and a zx over x cubed plus z. Now we want all of the things that have a zx on the same side. So I'm going to bring them all to the left. And I'm going to factor out a zx at the same time as well. So I have a zx times this term plus this term with the zx already pulled out, minus, bring that over, it'll be a 1 over x cubed plus 2. Right, so you distribute the zx3, you get that, minus that. Equal to this minus this term here. I don't have enough room. Okay. So, yeah. There's 2 more steps I have to do, unfortunately. So one of them is to just divide by this. So I suppose you could write your answer like this. You can totally write your answer as all that stuff. I might be able to fit this in here. Let's see if I can make it work. Like Tim Gunn says, make it work. Well, he used to say, he's not on that show anymore. They're on a new show. My wife is watching it. She does pretty good. Divided by all this. So the new one is more focused on their creative abilities and less on their ability to sew, although they still have to sew. Sorry, talking about TV, I should talk about math. So you can totally write it like this, and it's kind of gross. Usually what we do is we multiply everything by x cubed plus 2 over x cubed plus 2, so we don't have fractions in fractions, which is going to be kind of nasty. But I will say, if I'm going to simplify this so I don't have, like, I wouldn't multiply everything by x cubed plus 2, sorry, x cubed plus z. That's a z. Be careful, James. I would wait till the end if I was going to simplify. So multiplying this out, it's not quite as bad as it looks. When you do this times this, you're just going to get 3x squared. When you do this times this, okay, you're going to get minus 4x cubed z cubed times x cubed, so minus 4x to the 6th z cubed. And then this times this will be a minus 4x cubed times z to the 4th. Divided by, okay, so let's go from right to left. This times this will just give you a minus 1 at the end. And this times this we have to FOIL. So I'm going to have that times that is a 3x to the 7th z squared. And z times that is a 3x to the 4th z cubed. And then x cubed times that is x cubed y squared. And then z times that is y squared z. Blah. Okay, so Tara, that's probably a little grosser than I meant it to be. Sometimes it happens. And then you could do, I feel like we shouldn't, but you could do the same work to find, well, let me just, I will start the other one for you, and then you can do that on your own sometime. So I was going to find zy. Zy is actually a little bit better because there's less y's. So here the derivative is just x to the 4th times 3z squared zy. Here the derivative is, okay, we have to use the product rule there. It's going to be 2yz plus y squared times z prime, or zy. And it's going to equal, almost have enough room. It's going to equal the derivative of this, which is 1 over my stuff, times the derivative of this. The derivative of this in this case is just zy. So this one's actually a lot easier because we have a lot less terms. So you just have, right, this is the only term that doesn't have a zy in it. So you would bring this over here, factor out the zy, and divide by what's left over. Just a little gross.
Wait, James, so it's, for zy, it's x to the 4th times 3.
3z squared times zy.
Zy, and that.
And then the derivative of this, you have to use the product rule. For the derivative of this part, we get this piece and this piece. 2y times z plus y squared times zy. And then for the right-hand side, it's pretty straightforward. It's just 1 over the stuff times the derivative of this stuff, in this case, is just zy, because the derivative of x cubed is 0. And we could probably finish it if you guys want to. Who am I kidding? I want to. You guys know. Start a problem, we gotta finish it. Usually. So let's see here real quick. This isn't too bad. So I'm gonna leave this on its own. So I got 2yz over on the left-hand side. On the right-hand side, I've got, and again, let's factor out the zy. So the zy, zy, zy. So I'm gonna have zy times this minus this first term, which would be 3x to the 4th z squared. That's a 1, by the way. I know it doesn't look like a 1. It's a 1. And then, so I dealt with this, and now this, minus a y squared times zy. I'm going to factor out the zy. So then zy is just 2yz divided by all that. Okay, so 2yz divided by all this mess. 1 over x equals z minus 3x to the fourth z squared minus y squared. And then you probably would be better off multiplying by x cubed plus z over x cubed plus c to get on top 2x cubed yz, right? Just multiplying this by that, and then 2yz squared, right? Because it's z times 2yz. On the bottom, this times this is just 1. And then this times this, you have to do the whole foiling thing. So x cubed multiplies each part. You get minus 3x to the fourth z squared minus x cubed y squared. That's x cubed times each piece. And then z times each piece is going to give you a minus 3x to the fourth z cubed minus y squared z. These problems I feel like are a little more intense than you might actually be asked to do. I would hope, because I feel like they're kind of extra super gross. But that's the idea. You're always treating z as a function of x and y. So whenever you differentiate with respect to x or y, you end up getting zy or zx, whichever one. Okay. So, yeah. So eventually, I feel like I know Rademacher's class, he started talking about some sort of linear algebra stuff to prepare you guys for what we're going towards. So even though you might not be here yet, I think it's worth our time in these last 12 minutes to talk about where we're going. So a little bit of backup. Remember, you might remember from 17B, hopefully, that we solved some differential equations like the following, like dx dt is equal to a times x. And to be honest, I don't remember if we did this or not because my brain is tired. But the way we would have solved these would have been to separate variables. So we would have said, oh yeah, 1 over x dx equals a times dt. And then we would integrate both sides. And the integral of 1 over x is the natural log of the absolute value of x. We kind of ignore the absolute value. And the integral of a dt is just a times t. Let's see. And we're treating a like a constant. And so then solving for x, e to the this equals e to the that. E to the natural log of x is x. This becomes e to the at times e to the c. And then we usually call this a new constant. So we will call it just c again. So we will call it other things. So we get x as a function of t is some constant. I'm going to call it c again. It's pretty typical to call that constant just capital C. So don't be confused, right? This c and this c aren't the same exactly, but we're just saying it's a constant. I can call it c. But if you don't like that, you can call this one c1 and this one c2. If that one makes you feel better about them not being the same. So this is our general solution to this, right? We're saying, oh yeah, if I look at this function, right? So the derivative of this constant times e to the at, well, the derivative of a constant times the function is the constant times the derivative of e to the a times t is e to the stuff times what's the derivative of a times t? Oh, sorry, I made a small mistake here. That should be d dt. Because I'm differentiating with respect to the independent variable t. Apologies, that's a t. The derivative of e to the at is e to the at times the derivative of at, which is just a. And look, our x is that. So our derivative, I keep writing d dx, it's so natural. The derivative of our x is equal to our x times a. So we did indeed solve this differential equation. We found the solution to dx dt equal to x times a. So the idea moving forward is that we're going to solve multiple systems of linear differential equations. Specifically, two systems and two equations. So here is an example of that. So we want to solve the system. What have I got here? dx1 dt equal to x1 plus 3x2, and dx2 dt equal to 2x1 plus 2x2. With some initial conditions, x1 evaluated at 0 is equal to 2, and x2 evaluated at 0 is equal to -1. Okay, so we want to solve this. So we're trying to find x1 and x2 as functions of time that are solutions to this system of equations. And so what ends up happening is we end up having to find eigenvalues of a matrix, which is why we talked about eigenvalues last quarter. So we're going to look at the coefficient matrix, which is just the coefficients of these written as a 2x2 matrix. In fact, we can write the equation, as dx1 dt, dx2 dt equal to this coefficient matrix times this variable matrix. Right, that says exactly the same thing as this. It says dx1 dt is equal to 1 times x1 plus 3 times x2. dx2 dt is equal to 2 times x1 plus 2 times x2. And the idea behind the solution is that we're essentially still kind of saying, in fact, we kind of write this in this compact way, the derivative of this vector is equal to this matrix times the derivative of that vector. It's kind of the same equation as what we have on the other side here. It's kind of like saying, it's not exactly the same, but it's very similar to saying, I'm trying to solve the derivative of x is equal to a constant times x. Except now it's the derivative of this vector x is equal to this constant times this vector x. And so our solution is going to be something similar to, but not exactly the same as, x equal to c to the at. That's where our solution is going to end up living. It's going to be a little bit more complicated. All right, so here's how the solution actually works. The solution is given by, this is going to be kind of crazy, it's c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2, where c1 and c2 are constants we have to solve for. Lambda 1 and lambda 2 are the eigenvalues, and v1 and v2 are the corresponding eigenvectors of this 2x2 matrix. Okay, so I know it's been a while since we found eigenvalues and eigenvectors, but there's no time like the present. I feel like a fresh board, so I'm going to use the other board and I'll come back right on this side. My voice is starting to go. And by starting, I mean it's really starting to go. Okay, so here's our matrix. And the way we find the eigenvalues is by taking the determinant of the matrix minus lambda times the identity. Usually we just end up saying subtract lambda in the diagonal entries. More generally, right, it's the determinant of A minus lambda I, where I is the identity matrix, there's ones on the diagonal and zeros everywhere else. It means you subtract lambda diagonal. Okay, the way you find the determinant, it's, let me use some of my garbage pens. It's this times this minus this times this. So it's going to be 1 minus lambda 2 minus lambda minus 2 times 3 equal to 0. Multiply this out, I get lambda squared. Well, I'm doing it backwards, fine. I get lambda squared minus lambda minus 2 lambda is minus 3 lambda plus 2 minus 6. So I get lambda squared minus 3 lambda minus 4 equal to 0. So you get lambda minus 4 times lambda plus 1 equal to 0. So my eigenvalues are lambda equal to 4 and lambda equal to negative 1. Great. Fun times. So I will mention your eigenvalues are not always going to be nice. And in fact, most likely we are going to see imaginary or complex eigenvalues as we go further on. So just be prepared for that. There are going to be complex eigenvalues, most likely. So we've got lambda 1 equal to 4, lambda 2 equal to negative 1. But then we have to find the eigenvectors that go with them. So there's a couple ways you can find eigenvectors. The way I prefer, well, let's say, for 2 by 2 matrices, which is all we should have to deal with, there's usually a pretty straightforward way. Well, let me remind you. So if V is an eigenvector associated to the eigenvalue, all that means is that the matrix times the eigenvector is equal to the constant lambda times the eigenvector. That's what it means to be an eigenvector, is that the matrix, so basically the matrix multiplying the vector is just scaling the vector, right? It doesn't change the direction of the vector at all, it just changes the magnitude. So the way I like to do this is to say, okay, well, I'm going to try and solve A times my eigenvector, which I'm going to call V1, V2. And that's probably not great notation. Let's call it, so I'm already calling my eigenvectors V1 and V2. This one's V1, let's call them U1 and U2. Or X and Y, X, I don't care, it doesn't matter. Equals my lambda, which let's use lambda equal to 4 times the same vector. And then this gives you a system of 2 equations, and usually you only need one of them. So looking at the first equation, I get 1 times U1 plus 3 times U2 equal to 4 times U1. Right, I'm just doing that times that plus that times that equals 4 times that. I'm not even going to write down the second equation. And then I'm going to isolate U2 or U1. 3U2 equals 4 minus 1 is 3U1. So U1 equals U2. And then pick U1 to be any number you like that is not 0. I'm going to pick 1. Most times you pick the smallest integer so that things are all integers. So here, my eigenvector is the vector 1, 1. You could also say it's the vector 2, 2, or 5, 5, or a billion, right? Any 2 numbers there that are the same would be an eigenvector, because any eigenvector, any multiple of that is also an eigenvector. So you can check, right? If you do this matrix times 1, 1, you end up with 1 times 1 plus 3 times 1, 2 times 1 plus 2 times 1, which is exactly the eigenvalue times the eigenvector. So this vector 1, 1 is the eigenvector that goes with the eigenvalue lambda equals 4. And then you can do the same sort of thing for negative 1, which we'll do, and then we'll stop there. So for 1, 3, 2, 2 for, let's use W's this time, W1, W2. So I could also find the, oops, come on. So again, looking at the first equation, I get 1 times W1 plus 3 times W2 equals negative 1 times W1. Solving for W1 or W2, I don't know. 3W2 equals negative 2W1. So you can say negative 3 halves W2 equals W1. And then pick W2 to be something convenient. I'm not going to pick 1 because I don't want W1 to be negative 3 halves. I'm going to pick W2 equal to 2 because then if W2 is 2, W1 is going to be negative 3 halves times 2, which is negative 3. So here the eigenvector is negative 3, 2, or any multiple of that. All right, so we're out of time, but we'll continue talking about this on Wednesday. Definitely come with questions on Wednesday. There is a quiz to do. Make sure you fill out the attendance form if you didn't already. I'll throw it up there one more time. And yeah, I'll see you guys on Wednesday. Take care. Bye.
Thank you.
You're very welcome. Always. Happy to see you guys. I guess I should end the meeting.